Hey, so in section 1 of electromagnetism, we're looking at how charges behave in magnetic fields. And starting section 2, we're looking at how current-carrying conductors behave in magnetic fields. And the beautiful thing is that they do not behave any differently to the two just charges by themselves. So we said if a charge is moving inside a magnetic field, let's say the magnetic field is going into the page like this, then that charge will experience a force, and that force, actually, just for the sake of this demonstration, let's say it's a negative charge, it's moving in a magnetic field, then we just say we use the right hand push rule, where your thumb is the current, and current's against the direction of negative charge. So the current will be this way, fingers are the magnetic field, and I've got the magnetic field going into the page, and so the force is downwards. And so I see here the force is downwards for this example. And now this is the same for an electron floating by itself through the air or an electron inside a wire. So if I drew this as a wire and the wire had an electron inside it, the electron still experiences that force. The whole wire, in fact, is pulled down. And there's probably not just one electron, but quite a few electrons flowing inside this wire, all flowing in the same direction. And the whole wire is going to experience a force pulling it down in this magnetic field. You turn the electricity off, the electrons stop moving, and the force disappears. The faster the electrons move, the more force there is, normal sorts of things. Actually, yes, the faster the electrons move, the stronger the force. The more electrons there are, the stronger the force. And together, the speed and the number of electrons flowing through the wire is the current, I. So that's where this I comes in this equation. So the strength of force, F, actually, strength of force, F, force here, is going to be equal to a few things. The first one is L. L then I. L is going to be the length of wire that is inside the magnetic field. So it's only this amount of wire in the magnetic field. The parts outside the magnetic field are unaffected. So that's L. I is the amount of current. And the amount of current depends on the number of electrons and how fast they're going as well. And B is the strength of magnetic field, and I've already got some green magnetic fields going on here. B is the strength of magnetic field. And it makes sense that these three things control the strength of the force. You make a stronger magnetic field, those electrons are affected. You make a each electron is affected, so every electron is adding to the force. So if you increase this length, then you've got more electrons in that length. If you increase the current, you've still got more electrons in there as well. This equation is strongly related to the one we did in the previous video. F equals QVB. But now Q and V together kind of like our I and L. Yeah, because I is saying the number of charges, so the number of charges per area, so that's the current, and how fast they're going. Those two combined are in I. And L is, again, kind of saying how many charges. By increasing the length, you're increasing the number of charges in that area. Okay, and B is B, and they're just causing a force. It's the exact same force, and we call it the motor effect. Unsurprisingly, the motor effect is used in motors, electric motors, to make them move. These forces are the forces that we use in everyday machines. Anything that moves using electricity is using the motor effect. Okay, so we need to identify the conditions under which maximum force is produced. So you increase these three things, I, L, and B, you're increasing the force. But when they say maximum force, they're talking about the angles. So here you'll see it's also equal to, you'll see it's F equals Li as long as I is perpendicular to B. So again, there's that right-hand push rule. I is current, B is magnetic field, and they've got to be perpendicular to each other to achieve the full force. If they're not perpendicular to each other, then you're going to get have an angle. Theta is not going to be 90 degrees, and you need sine theta to work out exactly what proportion of the force you get. Conditions under which no force is produced on the conductor, that is when they're parallel to each other. So either your current is in the same direction as the magnetic field, or it's in the complete opposite direction to the magnetic field. Those are the situations where there's no force. And the relationship between the direction of force, magnetic field strength, and current, the directions of those three things can be explained again by the right-hand push rule. Current, what do we got? Direction of force is the push, magnetic field strength, the direction is the fingers, and current, the direction is your thumb. Really simple. It's just another example of the right-hand rule in place. Instead of just being on one charge, it's on lots and lots of charges. Lots and lots of electrons in this case. The only thing that you're going to stuff up by accident is going to be when you see the electrons moving, you've got to remember the current is in the opposite direction. It's the only thing. If for some reason they're positive charges moving, which we almost never see inside wires, then it's going to be the same direction as the positives. That's it. Nice and easy.